I want to now continue what we started last time. Essentially, I want to solve ODEs using series. Okay. In particular, I'll be focusing on second order linear differential equations. Okay, homogeneous. Okay, because essentially we have figured out essentially to begin with, many equations of interest are actually homogeneous. Okay, but even if you have a non-homogeneous equation, once you have the complementary solution, you can then construct for using that the particular integral as we saw last time. Okay, so I'll be focusing on homogeneous differential equations. Okay, and now what I'll do is that you given a differential equation, you assume that the solution to the differential equation can be written down as a powered series. So in other words, given the differential equation, I assume that the power that the solution can be written in this form. So this is known as a powered series. Okay, essentially is a series of consisting of polynomials. Okay, you expand y of x about the point x0, so you say that this series is centered about the point x0. Okay, and these a-n's of course are the coefficients in your series expansion. In general, this is an infinite series. It may truncate, it may not truncate depending on your differential equation. Okay, and the parameters that are there in your differential equation, as you will see. Okay, so of course, given a power series, there's always the convergence, the issue of the convergence of a power series. Okay, so the power series converges. Okay, for some values of x, it may converge for all values of x, as it converges from minus infinity to plus infinity, as is the case, for example, for the power series for e to the power x. Remember, e to the power x alternatively can be written in this form. Okay, so you have x to the power n divided by n factorial. And this power series converges for all values of x. On the other hand, you have some other series which does not converge for all values of x. Okay, and for some points, of course, you cannot write down a power series. So for example, for ln x, you cannot write a power series about the point x is equal to 0. Okay, because the function is not defined at x is equal to 0. Okay, so there's always the issue of convergence of a power series, right, as a power series about x not equal to 0. Okay, so you say, just as a terminology, you say that that a function is analytic at a point. What does this mean? It means essentially that the function can be written as a power series at that point. Okay, essentially, practically speaking, it usually just means that the function is well behaved at that point, so that the value of the function is well defined, its derivatives are well defined. Okay, so that you can then essentially do it in a series expansion. Okay, so for example, e to the power x is analytic at all points, but ln x is not analytic at x is equal to 0. Okay, but it is analytic at other values of x. Okay, so for example, it's analytic at x is equal to 1. Okay, fine. Now, given a second order differential equation, I can always, of course, write that differential equation as in this form, where these primes denote derivatives. Again, I'm focusing on homogeneous second order linear differential equations. Okay, so in general, these a's are functions of x. Okay, I can divide throughout this equation by a2. Of course, I'm assuming that a2 is non-zero, otherwise you have a first order differential equation. Okay, so okay, I'm dealing with linear differential equations as well. Okay, so essentially you have a double prime plus, I can write the second order linear differential equation in this form. Okay, of course, p of x is a function of x, which is just a1 divided by a2, and q of x is also a function of x, which is just a0 divided by a2. Okay, now you have to study such a differential equation. P of x, remember, can be any functions. They can be p of x, for example, can be x, it can be x square, it can be cosine of x. Okay, and so on and so forth. You have two kinds of points. You have ordinary points. So you have ordinary points for the differential equation, and you also have singular points. Okay. Ordinary points of the differential equation are those points at which p of x, this function p of x, and this function q of x are both analytic. Okay. So in other words, p of x and q of x, both of them are well behaved. Okay. So that's an ordinary point. Okay. If you don't have an ordinary point, then you just have a singular point. Okay. So for example, given this differential equation, so here's a nice second order linear differential equation. Okay. P of x is of course 0, q of x is minus x. Okay. Both of them are nice functions. Okay. With essentially you have trivial power series for both of those functions. Okay. The power series for p of x only contains a constant term which is 0. The power series for q of x only contains the term minus x. Okay. So essentially the point x is equal to 0 is essentially an ordinary point for your given differential equation. Okay. On the other hand, given this such a differential equation, x square minus 1 for example, okay, y double prime for example plus 2x y plus 6y is equal to 0. You first of all, to investigate whether you are dealing with any singular points or not, you just divide by x square minus 1 throughout to bring this equation to standard form. Okay, so you get this. Okay, and then you immediately see that okay, p of x can be represented to the power series. It's nice and continuous, except that it blows up at the points x is equal to plus minus 1, and same for q of x. Okay, so in other words, the points x is equal to plus 1 and x equal to minus 1 are singular points for this differential equation. Okay, but the point x is equal to 0 is an ordinary point. Okay, because the functions p of x and q of x for this differential equation are perfectly well defined for x is equal to 0. Okay, they're analytic. Okay, there's an important theorem. Okay, so most of the theorems over here I'll be doing without proof. Okay, because essentially doing the proofs is very difficult over here. It will take us a long time to do them. Okay, you have existence of solutions. Okay, so in other words, this says that for an ordinary point, okay, that's why I introduced the terminology. We can find two solutions, two linearly independent. Okay, solutions in the form of a power series centered at x naught, which is the point that you're talking about. So in other words, if you write down a power series about an ordinary point, okay, then you can just substitute this power series into the differential equation, solve it, and you'll automatically get two linearly independent solutions. Okay, that's guaranteed. And once you have two linearly independent solutions, of course, for linear differential equation, second order linear differential equation, you essentially just solve your homogeneous linear second order differential equation. Okay, fine. You also have that the solution that you find, the series that you write down for y of x, okay, this series is convergent. Okay, wait. This series is convergent for, so the series is convergent for x minus x naught less than r. Okay, at least this much convergent, where capital R is essentially the radius of convergence for the functions p of x and q of x. Okay, loosely speaking. Okay, so that's what we have. Okay, so if you have a second order linear differential equation and you identify, okay, you write down the power series about an ordinary point. Okay, then you can substitute that power series into your differential equation. Whatever power series you find as your solution, okay, you'll find two independent power series, okay, and so you have essentially found two linear independent solutions to your differential equation. Those power series are guaranteed to converge within some interval given by this, okay, and R is essentially the radius of convergence for P of x, the minimum between the radius of convergence of P of x and Q of x. Okay, let me explain what that means. This just means essentially that, for example, if you have this differential equation, okay, wait, where is it? This one, okay. So if you have this differential equation, you put it into standard form, you have this, okay, and once you have that, then you can just say, okay, P of x converges between -1 and 1, okay, because it blows up at x is equal to +1 and x is equal to -1, and Q of x converges between x is equal to +1 and x is equal to -1. So if you are expanding about x is about the point, you write down the power series about the point x naught is equal to 0, then this series is guaranteed to converge for all values of x such that mod x is less than 1. That's essentially because the radius of convergence for both P of x and Q of x is both equal to 1. Okay. If on the other hand you had something like this, x square minus 1 y double prime plus 2x y prime plus 6 x square minus 1 y is equal to 0. And of course you divide throughout by x square minus 1 and you have y double prime plus 2x over x square minus 1 y prime plus 6 y is equal to 0. And now whatever power series you find, those are also guaranteed to converge for mod x less than 1, because yes, q of course converges for all values of x, okay, because that's just a trivial constant function, but you have P of x which only converges for mod of x less than 1. Okay, so that's essentially what you have as far as the theory part of this solving series solutions using power series goes. Okay, you have to expand about an ordering point. Okay, check whether you're dealing with an ordering point, write down a series solution, substitute a series solution, the power series solution into your differential equation, and just solve for the power series. Okay, right. Okay, so before going on, let me just make a technical point. This is a power series. It's an infinite series of polynomials. Okay, each individual term is a simple polynomial. So this is a power series. This, on the other hand, for example, is an infinite series, but this is not a power series because each term is because it contains non-polynomial terms. Okay, right. So what I'm saying above is that if you have a second order linear differential equation, if you're interested in the solution of the differential equation around some ordering point, okay, then you write down, you assume that the solution is of the form of a power series centered about that ordering point, and in this way you just plug that power series into your differential equation. You are then guaranteed to find two linear independent solutions of the form of your assumed power series. Okay, but if you can also, as you'll see later on, also do a similar thing by expanding about a singular point, provided that the point that you are expanding about is not too singular. Okay, and I'll quantify what that means. If you expand it about a singular point, then the solution that you find, at least one solution, you are guaranteed to find of this form. This is an infinite series, but it's not a power series. Okay. Okay, with that in mind, let's just see how that works. Okay, how do we find out, first of all, solutions to order differential equations about ordering points. Okay, so for example, you have this equation, which is Airy's equation, one form of Airy's equation. This arises, for example, when you study diffraction of light, okay, and you just have to solve this second order homogeneous linear differential equation. Okay, so given what we know that this is essentially x is equal to 0 x is equal to 0 is an ordinary point, so we assume solutions of the form of a power series centered about that point. So I write down this, okay, then I say okay, y prime is equal to n is equal to 0 to infinity a n x raised to power n minus 1, and then y double prime is equal to n is equal to 0 to infinity a n minus 1 x raised to power n minus 2. I plug this back into my differential equation, so I have this differential equation. So I have n is equal to 0 to infinity, right, and I have a n minus 1 x raised to power n minus 2, and then you have minus x, n is equal to 0 to infinity a n x raised to power n is equal to 0, right? And now I to combine this into a single sum, okay, but I have to make sure of two things. First, the index starts from the same value, okay, so in this sum you have, and you have the sum starting from n is equal to 0. In this sum you have starting from n is equal to 0. The second thing I need to make sure is that you have x raised to power n appearing in both sums, okay. So over here you have x raised to power n, but you don't have x raised to power n over here. You have x raised to power n minus 2, okay. So I have to guarantee these two things before I can combine these two sums into a single sum, okay. Let's see how that works out. So remember, so the best thing to do is just to write down the first few terms of both the series, okay. So essentially the n is equal to 0 term for this series gives you 0 because of this n over here. The n is equal to 1 series gives you 0. The n is equal to 2, the n is equal to 1 term gives you 0 because of this thing. The n is equal to 2 term gives you something, okay, non-zero. So I can write down the first series. I can start it from n is equal to 2 to n is equal to infinity. n minus 1 x raised to power n minus 2, okay. Okay, and this thing I can write as okay, right, fine, okay. Okay, now let me just write down, essentially do a change of summation variable over here. So I'll define n prime is equal to n minus 2, right. So then I can write down the first sum as n prime equal to 0 all the way to infinity a n prime plus 2, and then you have n prime plus 2, and then you have n prime plus 1. So n minus 1, remember, is n prime plus 1, okay. And then you have x raised to power n prime, right, okay. And you have minus n is equal to 0 to infinity a n x raised to power n plus 1 is equal to 0, right. Now for the first sum, of course, I can change my dummy summation variable from n prime to n. So I have n is equal to 0 to infinity a n plus 2 n plus 2 n plus 1 x raised to power n minus n is equal to 0 all the way to infinity a n x raised to power n plus 1 is equal to 0, okay. Fine, right. Okay, now if you notice, the first series starts from x to the power 0, while this series starts from x to the power 1, okay. So one way of saying that is that the powers of x are not in phase, okay, so they don't start from the same value. The easiest way to fix that is to simply extract from this first sum the term corresponding to x raised to power 0. So let's do that. Corresponding to x raised to power 0, you have n is equal to 0, of course, so you have a2, and then you have n 0 plus 2 is equal to 2, and 0 plus 1 is equal to 1, so you have 2 1 x to power 0, and the rest of it I write as n is equal to 1, okay, to infinity a n plus 2 n plus 2, n plus 1, x to power n, minus 0 infinity a n power n plus 1, and this is equal to 0. Okay, now over here I have exponent n plus 1. I need to make this n. Okay, so now I define n prime is equal to n plus 1. Okay, so over this, for this sum, when n is equal to 0, n prime is equal to 1, n is equal to infinity, n prime is equal to infinity, and instead of a n I have a n prime minus 1, and x raised to power n plus 1 is of course x raised to power n prime. Okay, and then I can relabel the n prime again to simply n. Okay, so you have a n minus 1 x raised to power n. So all in all I have 2a2, because x raised to power 0 is of course 1, plus n is equal to 1 to infinity a n plus 2, n plus 2, n plus 1, x raised to power n minus 1 to infinity a n minus 1, x raised to power n is equal to 0. Okay, now finally I am able to group these last two series as a single series. Okay, so finally I am able to get 2a2 plus n is equal to 1 to infinity, right? And then I have a n plus 2, n plus 2, n plus 1 minus a n minus 1, x raised to power n is equal to 0. Okay. For this to be identically equal to 0, we of course must have that a2 is equal to 0, and also that a n plus 2, n plus 2, n plus 1 must be equal to a n minus 1. So in other words, a n plus 2 must be equal to a n minus 1 divided by n plus 1, n plus 2. This is our recursion relation. This specifies the coefficients in your power series in terms of some initial coefficients. Okay, so this is your recursion series. Okay, and we have also found that a2 must be equal to 0. Okay, so let me put n is equal to 1 into the recursion series. I'll find that a3 is equal to a0 over 2, 3. Okay, right? And so let's just write it out. A4 must be equal to I'm putting n is equal to 2, so this must be equal to a3. I'm putting n is equal to 2, so this should be a1 over 3, 4, right? A5 must be equal to n is equal to 3 over here, so you get 2 over 3, so 4, 5, and this is equal to 0, because remember a2 is equal to 0. Okay, this condition over here. Okay, a6 must be equal to so n is equal to 4 over here, so n is equal to 4, so this is equal to a3 over a3 over 5, 6, right? Okay, so let's just find everything in terms of, let me do a few more. A7 will be equal to n is equal to 5 over here, so this is a4, and then you have 6 and 7. Okay, so the pattern is pretty clear. Okay, right? And then a8 is equal to n is equal to 6, so you have a5 over here, and then you have 7, and then you have 8, but this is equal to 0. Okay, right? So in other words, you don't know a0, you don't know a1, you know that a2 is equal to 0, then you know that a3 is equal to, in terms of a0, this is simply equal to a0 over 6, right? And then you have a4 is equal to a 1 over 12, and you have a5 is equal to 0. You have a6 is equal to a3 divided by 6, 5 is equal to a0 over 6, 5, and then a3 was of course 3, 2. I can write it like that, okay. And so this is a6, and then you have a7 is equal to a4 divided by 6, 7. This is a1, 7, 6, and then you have 4, 3, and a8 of course is equal to 0, okay. So a2 is going to be 0, a5 is going to be 0, a8 is going to be 0, a11 is going to be 0, and so on. The rest of it, of course, I can write as that y x is equal to a0 plus a1 x plus a2 x cube plus a3 x cube plus a4 plus and this of course now I can write as a0 plus a1x plus a2 is 0, a3 is a0 over 6x cube plus a4 is a1 over 12 x raised to power 4, a5 is 0, a6 is a0 over 30 times 3 is 90, 90 times 2 is 180, right? A6, and then you have 6x raised to power 6 plus a7 is a1 over 7 times 6 is 42, 42 times 4, well, whatever you get, okay. So 42, 4, 3, and you have x raised to power 7 plus, and so on and so forth, okay. So the point being, I can group terms that contain a0, so I'll get 1 plus x cube over 6 plus x raised to power 6 over 180 plus blah 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 plus a1 x plus x to power 4 over 12 plus x to power 7 over 42 times 12 plus, and that's it. As claimed earlier, since we are expanding about an ordinary point, your solution is the sum of two power series, okay, this one and that one, and these are linearly independent, okay, as you can check, okay. And of course these just serve as that's just there because essentially you are dealing with a linear second order equation, so you must obey the principle of superposition. Given one solution, any multiple of that solution is also a solution. Given another solution, any multiple of that is also a solution. The sum of these two solutions is also going to be a solution, okay. So that's what you have, and of course you have two undetermined constants over there, okay. Now, just like you can define the exponential function as a power series, so here you can write 1 plus x square over 2 factorial plus x cube over 3 factorial and so on. You can define these, you can give this power series and this power series some new names, okay. So for example, you can call f1x as 1 plus x cube over 6 plus x over 6 over 180 so on, and f2x is defined as x plus x to the power 4 over 12 plus x to the power 7 over 42, 12, and then so on, okay. Right, so essentially, so you are essentially dealing with special functions, okay. These are functions which are defined which are usually arise as solutions of differential equations. You define them in terms of a power series, okay, and it's useful to give them a name because they occur so frequently in applications, okay, whenever you're dealing with the associated differential equation, okay. If you notice, you can also form, for example, you can also form linear combinations of these functions f1 plus f2. This is also going to be a solution of your differential equation. And you can also form, for example, f1 minus f2. If it turns out that f1 plus f2 is linearly independent from f1 minus f2, then alternatively you can take this as one solution, this as another solution, then the superposition of these two solutions is also a solution. If you want, you can give this a new name, g1, this is g2, so c1 g1 plus c2 g2 is also a solution of your differential equation, okay, right? So it depends on essentially what kind of what function do you want to use to generate your all your solutions, okay. Okay, let us now look at another example. This is Legende's differential equation, okay. This occurs very frequently when you are dealing with problems which have some spherical symmetry, and you use spherical coordinates to simplify your life, and then you end up with the so-called Legende's differential equation, okay. It looks of the form 1 minus x square y double prime, okay, minus 2x y prime plus L and L plus 1 is equal to 0, okay. This L may or may not be the integer. Usually it is, as we'll see, okay. But right now just take it as a real number, okay. Now again we put this into standard form. So we have an ordinary point, x is equal to 0 is an ordinary point, okay. So we expand, we write y as a power series about that point, so we write, okay, physically x is very often the cosine of some angle, so you use spherical polar coordinates. X usually represents cosine of theta, okay, where theta is your usual spherical polar coordinate that goes from 0 to pi, okay. So essentially you want your solution to be converging on the interval, since you are dealing with from cosine of 0 to cosine of pi, okay. You usually want your solution to be converging between minus 1 and 1, including the points minus 1 and 1, because those represents your your poles in spherical polar coordinates, okay. So anyway, you assume this power series, and then you play around. Essentially you have y prime is equal to n is equal to 0 to infinity, and then you have n x raised to power n minus 1, y double prime is equal to n is equal to 0 to infinity n minus 1 x raised to power n minus 2, right? Fine. And then I have that you just plug these back into your differential equation. So you have y double prime, right? So you have n minus 1 x raised to power n minus 2 minus x square multiplied by y double prime, so that gives you n minus 1 x raised to power n. Then you have minus 2 x times y prime, that gives you n is equal to 0 to infinity n x raised to power n, right? And then you have plus L times L plus 1, and then you have y is equal to 0 to infinity n x to power n. This has to be equal to 0, okay. Then what do we have? I can
start the first term from n is equal to 2. The first sum we can start from n is equal to 2 and then do a change of variables. Okay, that will give me so that my sum contains x raised to power n instead of x raised to power n minus 2. So looking at the first term, by now we know how to do this. You write the first term as n is equal to 2 to infinity a n minus 1 x raised to power n minus 2. Then you define n prime is equal to n minus 2. So you have essentially that this thing is equal to n is equal to 0 to infinity a, and then you have n prime plus 2, sorry, n prime over here, and then you have n prime plus 2, n prime plus 1, and x raised to power n prime. And this, of course, I can just remove the primes, and you have, okay, so you just plug this back now, and so then you can now remember that the first sum, now this sum, which is this sum, contains x raised to power n. It starts from n is equal to 0. This sum starts from n is equal to 0, contains x raised to power n. This sum starts from n is equal to 0, contains x raised to power n. This sum starts from n is equal to 0, contains x raised to power n. So essentially I can group everything as a single sum now. So the left hand side now becomes n is equal to 0 to infinity, and I have a n plus 2, n plus 2, n plus 1, right, minus n a n minus 1, right, minus 2 n a n plus l plus 1 a n x raised to power n. This is equals to 0. If this has to be identically equal to 0, then of course this term in the square brackets has to be equal to 0. Okay, so you essentially immediately get that a n plus 2 n plus 2 n plus 1 is equal to a n. Then you have 2n plus n minus 1 minus l plus 1. Okay, so you have a n plus 2 is equal to a n 2n plus n plus n minus 1 minus l plus 1 divided by n plus 1 n plus 2. That is your recursion relation. Okay, I can simplify the numerator somewhat. Okay, so I have 2n plus n square minus n, so this gives me n square plus n minus l plus 1 divided by n plus 1 n plus 2, and this is equal to a n square minus l square, right, plus n minus l. Okay, and this is equal to a n, and you have n minus l, n plus l, of course, plus n minus l, and finally you have that a n plus 2 is given by a n multiplied by, you just factor out n minus l, so then you're left with n plus l plus 1. So this is the form in which the recursion relation is usually written. Okay, so now again, if you have a naught from this recursion relation, you can get a2, a4, a6, a8, and so on, all the even coefficients in your power series. If you have a1, you can get from this a3, a5, a7, and so on. Okay, right? So essentially you just say, okay, if I have a naught, what do I get as a2? I get essentially a2 is going to be a naught. You just plug in values over there and you'll get, okay, n is equal to 0, so you get 0 minus l, you get minus l, and then you get l plus 1, right, divided by 2. Okay, so that's what you have. So a2 is equal to minus l L plus 1 over 2. Okay, and then you have A4, you can find similarly is going to be given by L minus 2, L L plus 1, L plus 3 divided by 4 factorial. Okay, so A times A naught. Okay, and so on and so forth. Okay, so you can write that before doing that, let's do it for A1 to A3. So A3 is going to be given by A3 is going to be given by minus L minus 1, L plus 2 divided by 3 factorial A1. Okay, and then A5 is similarly L minus 3, L minus 1, L plus 2, L plus 4 divided by 5 factorial, and so on. Okay, so in other words, just like we did before, you can group terms, all the terms that contain A naught, you can group the terms, all the terms that contain A1. So you can write that my y of x is simply equal to A naught multiplied by 1 minus L plus 1 over 2, just write 2 factorial. Okay, x square, right, plus this A4 term L plus 1, L plus 3 divided by 4 factorial x to the power 4, and so on, right, plus A1 A1, and then you have x. Okay, and you have A3 minus L minus 1, L plus 2, 3 factorial x cube. Then you have A5. Okay, so I can write this solution as A naught y1 plus A1 y2, where y1 is this power series in the first square bracket and y2 is the power series in the second square bracket. Okay, fine. So that's my solution to the differential equation, except that there's a problem when you come to applying this physically. So y1 and y2 you can call as Legendre functions. Okay, the problem is essentially that both of these power series diverge when x is equal to plus minus 1. So they converge, the power series converge over the open interval minus 1, 1. So when x is from minus 1 to 1, not including the points minus 1 and 1, that's why I'm calling it an open interval, your series converge and you have perfectly nice solutions. They are infinite series, okay, but they converge, okay. But when x is equal to 1 or x is equal to minus 1, you can check by applying the convergence test on these series, okay, ratio test for example, that this series will diverge for x is equal to plus 1. It also diverges for x is equal to minus 1 for arbitrary values of L in general, okay. However, if L is an integer, if L is a positive or integer, okay, or 0, okay, then what happens? Let's see. Well, if L is 0, then if you notice this thing, if L is 0, y1 is simply 1. Okay, so if L is 0, y1 is simply 1. The other terms are just equal to 0. There's L over here, that gives you immediately 0. There's L over here, that immediately gives you 0. And in the other terms as well, you get L. Okay, that should be obvious because you have this recursion relation, right? If A2 is 0, then it's guaranteed that A4 is going to be 0. If A4 is 0, then it's guaranteed that A6 is going to be 0, and so on and so forth. Okay, right. So it's interesting to see what happens when L is an integer. Okay, what happens when L is equal to 1? before doing that, what happens to y2 if L is equal to 0? Well, y2 does not converge. Okay, so y2 remains an infinite series, okay, which is actually divergent at the points x is equal to plus minus 1. I need it to be convergent actually physically at the points x is equal to plus minus 1, because like I said previously, usually x corresponds to the cosine of some angle, the cosine of the spherical polar coordinate. Okay, so and you of course you want solutions to exist at the poles, okay, which correspond to cosine of 0, which is 1, and cosine of pi, which is minus 1. Okay, right, so this is a perfectly valid solution now to your differential equation, because this is convergent. Of course, that's just the constant term. L is equal to 1. Well, if L is equal to 1, this thing, the first one, y1 is an infinite series, which is again divergent. However, y2 is very simply, because this thing becomes 0, so you get a3 is equal to 0, and then a5 is going to be 0, and so on. Oh, sorry, there should be x raised to power 5 over here. Okay, so now it's y2 which is truncating. So y2 is simply equal to x. Okay, fine. If L is equal to 2, then what? If L is equal to 2, you get, this is non-zero, of course, this is non-zero, but this is 0 because of this term. So if a4 is 0, then a6 is 0, and so on. Okay, so you simply have 1, y1 is equal to, if you go up, right, if you go up, what you get is that you have 1 minus L multiplied by L plus 2, L plus 1 over 2 factorial. So you have 1 minus L over L plus 1 over 2. Okay, so, and the multiply by x square, of course. Okay, right. y2 on the other hand gives you an infinite series, which is again divergent at x is equal to plus minus 1. So in other words, if you have integer values of L, then your solutions to the differential equations, okay, which are convergent at the points x is equal to plus minus 1, are actually a set of polynomials, which are called the Regenitive Polynomials. Okay, these polynomials are essentially denoted in the following form. You write P, Regenitive polynomial, then you write a subscript which denotes what value of L you are talking about. So, and you write as this. So this is simply equal to 1. Okay, P1x is equal to x. Okay, P2x is equal to 1 minus L plus 1 over 2 x square. Okay, but of course L is equal to 2, so you can simplify this further. So you have 2 multiplied by 2 plus 1 is 3, 6 divided by 2 3. Okay, except that you don't, so given one of these Legendre polynomials, you know that it is a solution, and then any multiple of such a Legendre polynomial is also a solution. Okay, because you are dealing with a linear differential equation. Okay, so usually you use a convention to normalize these Legendre polynomials. Essentially, this just means that you set any, you essentially multiply these polynomials by a constant such that you get this. Okay, so that you have essentially that the value of the polynomial at x is equal to 1 is simply equal to 1. For, you can see that okay, for L is equal to 0, that is already satisfied. Okay, so you are essentially kind of rescaling all the other Legendre polynomials to this 0th order polynomial. For x is equal to 1, that is also satisfied. For x is equal to, sorry, for L is equal to 1, that is already satisfied. For L is equal to 0, you have the constant. For L is equal to 2, well, it's not satisfied, because for x is equal to 1, you get essentially minus 2. Okay, but I can then divide this by minus 2. Okay, so I can instead redefine my P2x as this thing. This is also going to be a solution, of course. Okay, because remember, you're dealing with a linear differential equation, and you can now check that x is equal to, when x is equal to 1, you have 1 minus 3, which is minus 2, divided by minus 2, which is 1. So I can write P2x is equal to half of 3x squared minus 1, and so on for higher order, higher values of L. Okay, so you have all these set of Regenitive polynomials. Okay, so much for ordinary points. Okay, I now want to talk about differential equations for which infinite series solutions exist, but then you are expanding about a singular point. So for example, you have essentially so for example, you can have an equation of this form: 3x y double prime plus y prime minus y is equal to 0. Okay, can I find the solution to this equation in this form? Okay, so you're expanding about the point x is equal to 0. Notice that x is equal to 0 is a singular point for this equation. Okay, in general, the answer is no. Okay, you need to generalize this power series. Okay, so first of all, you divide your singular points into two categories. You have your regular singular point, and then you have irregular singular point. Okay, if you have a regular singular point, okay, that means that you have a singular point, but it's still manageable. You can still find a solution about that point. Okay, but if you have irregular singular point, then you basically raise your hands, okay, and try to do it and hope for the best. It's not good, probably not going to work. Okay, for a regular singular point, on the other hand, what's a regular singular point? So first of all, once again, you write down your differential equation in the standard form. Okay, regular single point means that, of course, at that singular point x naught, px, of course, is not well behaved. Q of x is not, may not be well behaved. Okay, one of these two at least is not well behaved. Okay, that's why it's a singular point. On the other hand, if this is well behaved, it's analytic, and if this, oh sorry, let me just be consistent. If this is well behaved, okay, then you have a regular singular point, right? So for example, this equation that I talked about above, there is a singular point at x is equal to 0, but that's a regular singular point. Why? Because p of x is 1 over 3x. So if I multiply by x, then I simply get 1 by 3. That's a nice constant function. Similarly, q of x is minus 1 by 3x. If I multiply by x square, I'm going to get minus 1 by 3 times x. That's a nice linear function. Okay, nothing is blowing up over here. So x is equal to 0 is a regular singular point. Okay. So Frobenius theorem then says that if you have a regular singular point, so this deals with the regular singular points. Okay, it says that if you then use this substitution, so if you have a regular singular point at x naught, you can find your solution to your differential equation about x naught. You can find at least one solution of this form. Let me just write it out. So you have a power series multiplied by another factor where r is constant. Okay, so r is a constant. Okay. Which you need to determine. So there's another thing that you need to determine over here. But the important thing is that r need not be an integer. Okay. So for example, you might be dealing with, okay, how does this situation arise? Suppose you have something like this. Then you can write down the power series for this thing. So you have 1 plus x square over 2 factorial plus so on. And so you have x raised to power 1 by 2 plus x raised to power 3 by 2 plus x raised to power 5 by 2 divided by 2 factorial and so on. Right? Okay, so this thing is very similar to that thing. Okay, except that r is equal to 1 by 2, x naught is equal to 0, and of course this thing corresponds to the usual power series expansion for your exponential function. Okay, so essentially you're dealing now with some kind of generalized power series in which the powers need not be indeed positive integers. Okay, the r can be any number. Okay, right. So essentially the idea now is that if you are dealing with a differential equation, if you are looking for solutions about a singular or about a regular singular point, then you assume solutions not of the form of a simple power series, but rather a more generalized power series which looks something like this. Okay, and then from this you plug that into your differential equation, you do the differentiation as before, and then from what you get you try to figure out first of all the value of r, and then from the value of once you have the value of r, then you play around and find out the value of these coefficients. Okay, so first of all I can write down y in another form, relatively simple form probably. So this is I can pull this factor inside this sum. So I have an x minus x naught n plus r. Okay. Notice also, by the way, that we said that a naught is not equal to 0. Okay, so you start the sum from the term corresponding to n is equal to 0. Okay, it does not really gives you anything new if you don't start it from n is equal to 0, because then essentially you're just redefining the value of r. Okay, right. Okay, now the best way to learn how to apply this so-called Frobenius series to solving differential equation, this general infinite series, is just to do a simple example. So let's take the example that I introduced above. Okay, this differential equation over here. So you have 3x and you have you have 3x y double prime plus y prime minus y is equal to 0. Let's see. Right, that's fine. Okay, so we assume that you have a solution of this form. Remember that you are guaranteed that there's at least one solution of this form. X is equal to 0 is a regular singular point, so I look for an expansion about that point of this form. Okay, remember, if you can find one solution of such a form, that you can always find out the other solution. Remember the last video that we had. Okay, so we have, if you find one solution to your homogeneous second order linear equation, you can always find out the other linearly independent solution. Okay, so it might be the case that both solutions are of this series form. Okay, it may not be the case. Let's see. Okay, anyway, so you first of all, of course, you differentiate, and then you have n is equal to 0 to infinity, you have a n, then you have n plus r, and then you have x raised to power n plus r minus 1. You also have y double prime is equal to n is equal to 0 to infinity, a n plus r, and then you have n plus r minus 1, x raised to power n plus r minus 2. So far very straightforward. Okay, fine. And then I plug these two
derivatives into my differential equation. So I have 3x times y double prime. So I have 3n is equal to 0 to infinity an n plus r n plus r minus 1 x raised to power n plus r minus 1 because I multiplied by x. Okay, and you have over here plus n is equal to 0 to infinity. You have over here an n plus r x raised to power n plus r minus 1, and then you have minus, of course, n is equal to 0 to infinity an x raised to power n plus r, and this whole thing has to be equal to 0. Okay, so far so good. And now I can factor out x raised to power r throughout. So I have over here x raised to power r, and then I can write down the rest of the thing as a series. Okay, so you have 3 n is equal to 0 to infinity, and you have an n plus r n plus r minus 1 x raised to power n minus 1. Okay, then I have plus n is equal to 0 to infinity, and I have an n plus r x raised to power n minus 1 minus n is equal to 0 to infinity x raised to power an, and you have x raised to power n, and this whole thing has to be equal to 0. Okay, okay, so then we can because this has to hold true for any value of x, this thing in the square bracket has to be equal to 0. We also know that in the first sum, the first term that contains x corresponding to n is equal to 0 is x raised to power minus 1. And over here, this thing also starts with x raised to power minus 1. This thing, on the other hand, starts from x raised to power 0. Okay. So what I can do first is that I can peel off the n is equal to 0 terms. Okay. So that all three sums that I find in the square brackets, all three of them start from x raised to power 0. Okay. And then I can play around, of course, with the summation index such that I can combine all the sums into one single sum. Okay. So I peel off from the first sum the term corresponding to n is equal to 0. I'll get a naught r minus 1. Okay. Then I peel off the term corresponding to n is equal to 0 from the second sum to get a naught r, right, and that's it. Okay, so you have over here right, equal to minus 1, right, so I have right, n is equal to 0, and these things are multiplying with x raised to power minus 1. Okay, and plus I have from here the rest of the thing x raised to power r, and then I have the rest of the sum that corresponds to that goes from n is equal to 1 to infinity. So you have n is equal to 0 to infinity 3an, this goes now from n is equal to 1, 3an n plus r minus 1 x raised to power n minus 1. Okay, plus you have over here n is equal to 1 to infinity an n plus r x raised to power n minus 1, and then you have minus n is equal to 0 to infinity, you have an x raised to power n. Okay, this has to hold true for all values of x, so we must have that first of all 3a naught r minus 1 plus a naught r has to be equal to 0. Because we are assuming that a naught is not equal to 0, I can divide both sides of this equation by a naught, and I'll get 3r minus 1 plus r is equal to 0. Okay, so otherwise I have 3r squared minus 3r plus r, which is minus 2r, is equal to 0. Okay, this quadratic equation is an example of the so-called indicial equation. Okay, r is known as the indicial roots, there are always two values of r. They may be the same. Okay, so you have a repeated root because the initial equation always comes out to be a quadratic equation. Okay, the roots of the initial equation of course gives you the possible values of r. Okay, so the initial equation allows you to find the values of r that go into your series expansion. Okay, so you have, if you solve this initial equation, you get two roots. One is r is equal to 0, the other is r is equal to 2 by 3. Okay, so far so good. And then of course you also have that this time in the square brackets over here, this square bracket also has to equal to 0. Okay, the first two sums of course have the x raised to power n minus 1 in them, while the last one contains x raised to power n. But never mind, okay, the sum over here starts from n is equal to 1, the sum over here starts from n is equal to 0. Okay, the first term over here corresponds to x raised to power 0, x raised to power 0, x raised to power 0. So I should be able to bring them all in the form of a single sum by doing a change of summation index for the first two sums. Okay, so again I can define n prime is equal to n minus 1, play that whole game again that you should be familiar with now. Write down the first sum in terms of n prime rather than n, and then go back to n. Okay, so if I do that, I'll find that the sum can be written as n is equal to 0 to infinity 3a n plus 1 n plus r plus 1. Okay, because I'm replacing n with n plus 1. And you have over here n plus r, okay, and you have x raised to power n plus, do exactly the same game over here. You have a n plus 1 n plus r plus 1 x raised to power n, and then you have minus n is equal to 0 to infinity a n x raised to power n, and this whole thing has to be equal to 0. Okay, and then I can group this into a single sum. So I have over here 3a n plus 1, right, or okay, n plus r plus 1 n plus r plus a n plus 1 n plus r plus 1 minus a n, okay, x raised to power n, and this has to be equal to 0. Okay, so this has to be true for any value of x. So this thing in the square brackets has to be equal to 0. Okay, so I can rewrite this, I can factor out a n plus 1 and n plus r plus 1 from the first two terms. So you have a n plus 1 n plus r plus 1, and then I have 3 n plus r plus 1. That's my first two terms, minus a n has to be equal to 0. Okay, so then I have a n plus 1 n plus r plus 1, then I have 3n plus 3r plus 1 must be equal to a n. So I have then that a n plus 1 is equal to a n divided by n plus r plus 1 3n plus 3r plus 1. Okay, so this then is your recursion relation. But notice now that the recursion relation contains r. But never mind, we have found the possible values of r, remember? Okay, so you substitute these values of r 10 by 10 and then generate your sets of coefficients. And those sets of coefficients, of course, determine your infinite series. And once you have your infinite series, then you have the solutions. Okay, so let's see how that works out. So you again, you have two cases. You have r is equal to 0, r is equal to 2 by 3. Okay, if I look at r is equal to 0, then what do I get? I can generate some coefficients. So I start from a0. Then using the recursion relation, I have a1, because you have in the recursion relation you are now putting r is equal to 0. You have a1 is equal to a0 divided by n plus 1, but n is 0 over here, so you have 1 and 1, so a1 is equal to a0. And you also have then that you can then generate a2. Okay, so you have a2 will be equal to a1 divided by n plus 1, which is 2, and then you have put n is equal to 1 over here, so you have 3 plus 1, which is 4. Okay, so you have 4, and you have a1 over 8, which is a0 over 8, and so on and so forth. Okay, you can play a similar game with r is equal to 2 by 3. Okay, and you can then get, for you start from a naught, you get a1 is equal to, I think, a naught over 5, okay, and so on and so forth, okay, just using the recursion relation. The point being that at the end of the day you will be able to generate two solutions, y1 and y2. y1 is written as n is equal to 0 to infinity an x raised to power n, okay, or n plus r1, okay, except that r1 is equal to 0, so we'll just write this is actually a power series of this form with these coefficients an determined by these coefficients and so on, okay. So you have a3, a4 and a5 of course as well, okay. y2 on the other hand is given by n is equal to 0 to infinity an x raised to power n plus r2, where r2 is of course 2 by 3, and these coefficients, these ans, are determined by these set of coefficients, okay, the ones generated by the recursion relation, but the recursion relation has r is equal to 2 by 3 inside, okay, and these two are linearly independent solutions in this case, okay. So in this case it turns out that both of your solutions are of the form of an infinite series, okay. Now going through the whole thing again, really the only thing new that you have when you go to infinite series, okay, the Frobenius method, is the initial equation, okay, and the initial equation, remember, is a quadratic equation, okay. So for example, we had an initial equation above, okay, here's the initial equation. It's a quadratic equation, so you have two roots, okay. I'll assume that the two roots are real, okay. We won't really be dealing with the case where they can be complex, but they can be complex. I can extend the theory to that as well, okay. But I'll assume that two roots are real, okay. And since it's a quadratic equation, you have different cases that you have to deal with. Remember, you have to, and you are looking for two linearly independent solutions at the end of the day, okay. You are guaranteed that one solution will be of the form of an infinite series. The question is, what's the form of the other solution, okay. So you have different cases. You have three cases. You have case 1, in which your initial equation has two distinct roots, okay, and these do not differ by any integer, okay. So this is exactly the case that we were doing above, okay, because one root was 0, the other root was 2 by 3, the difference between them is not an integer, okay. In this case, you are guaranteed that both solutions, y1 and y2, will be of the form of an infinite series, okay, of the form essentially an x minus x naught raised to power n plus r sum, okay. Then you have another case, okay, case 2, which you have two distinct roots. You don't have a repeated root, okay, but these differ by an integer now, okay. So for example, one root can be 0, the other root can be 2, okay. In this case, y1, one of the solutions, of course, will be of this form, where r1 is one of the roots. But then y2, the second solution, will be in general be of this form. Some constant multiplied by y1, the first solution, multiplied by ln x, plus an infinite series. Okay. Oh, I should be putting x minus x naught over here. Okay. So you have a logarithmic term, okay, in your solution as well. This logarithmic term can be 0. It can turn out that this capital C is 0. Okay. So then you have the solution, that the second solution is also the form of an infinite series. Okay. Right. So essentially, if you have two distinct roots which differ by integer, both solutions can be of the form of the infinite series, Frobenius series. They may not be. Okay. It depends from case to case. Okay. Case 3 is then you have your initial equation has repeated root. Okay. In this case, one solution is guaranteed to be of this form, but of course R1 is now equal to R2. Okay, and the second solution has to have a logarithm inside it. Okay. So in the previous case, when you had two distinct roots, they were different by an integer, it might, the second solution may contain this logarithm term, it may not, okay. But when you have a repeated root, it's guaranteed to contain this logarithm term, okay. I should also make it clear that I was labeling the roots R1 and R2 such that R1 is bigger than R2. Okay, when they are distinct, of course. If they are not distinct, then of course R1 is equal to R2, okay. So that's what we have. So you essentially have that you can find the solutions, okay, to any differential equation, linear second order homogeneous differential equation. That's the form of your solutions. It's good to know what to expect beforehand. Okay, what kind of solutions can we expect? Okay, so for example, if you are looking for solutions to x with x naught is equal to 0, you're looking for solutions about the point x is equal to 0. Okay, then of course you look for expansions, a power series expansion about that point. Okay, and then you find, okay, then you are happy that, okay, if you find, for suppose you so look at the initial equation, you find that R1 is bigger than 0. Okay, so then you find, okay, that this thing will probably be y1 will probably be a nice enough function. Okay, but then you say, okay, when I come to y2, that may not be such a nice function. Okay, it might be the case that this logarithm term still survives. Okay, it might be the case it disappears. If it disappears, well and good, but if it survives, then usually physically you run into some trouble. Okay, because then because x naught is equal to 0, then you're dealing with ln of x. Okay, and then usually you're also looking physically for the solution at x is equal to 0 as well. Okay, but then you know that ln of 0 of course blows up. Okay, so that does not correspond to physical solution then. Okay, so that's the whole point behind knowing beforehand what kind of solutions you expect. Okay, so you kind of expect, okay, that whether the solution makes physical sense beforehand or not. Okay, so finally, just to wrap it up, let's do one final example. You have the so-called famous Bessel equation. Okay, Bessel's equation. Okay, this is a differential equation of the following form: plus x y prime plus x square minus nu square y is equal to 0. Okay, Bessel originally looked at this when he was studying elliptical planetary orbits. Okay, but generally it also arises whenever you have some kind of cylindrical symmetry. Okay, so whenever you are dealing with a spherically symmetric situation, you usually end up with a Legendre equation. When you're dealing with cylindrical symmetry, you end up with the Bessel equation. Okay, and it rises all over the place. Okay, in thermodynamics, heat transfer and acoustics and so on and so forth. Okay, the solutions for the Bessel equation, surprise are known as Bessel functions. Okay, so again, just like you have sines and cosines, those are solutions of second order differential equations. Bessel functions are essentially solutions of this equation. Okay, you have two Bessel functions. You have Bessel function of the first kind and Bessel function of the second kind. These are two linearly independent solutions. Okay, this linearly independent functions which are solutions of this Bessel equation, and you can look up the properties of these functions. Okay, this nu, by the way, is a parameter. Okay, so this is nu is usually assumed to be nu is a real number bigger than or equal to 0. This is known as the order of your Bessel equation. Okay, so just to give you a brief introduction, okay, of how do you deal with such an equation. Okay, so remember, you first of all you put this differential equation into standard form, you divide throughout by x square, and then you find that, okay, that x is equal to 0 is a regular singular point. Okay, so then you can look for solutions of this form about x is equal to 0. Okay, and once you plug this thing back in, you can easily check that the value of r from the initial equation that you get is that you have two values of r. You have plus nu and minus nu. Okay, so it's not that complicated over here. So the initial equation gives you the two roots. Okay, and so the properties of your solutions depend then on what this nu is. Okay, if nu is an integer, okay, if nu is not an integer, okay, so for example it's something like 2 by 5, okay, and then you have minus 2 by 5. Those are the two roots, okay. The difference between them is not an integer, okay. So then you are guaranteed that both solutions will be of this form, okay, right. So you will have one power series, okay, which we denote as j nu x, okay. This is the solution of this Bessel equation, okay. You can write down the infinite power series for that. I'll leave that as homework for you, okay. I'll actually make you do that as your homework, okay. The other solution, of course, corresponds to j minus mu x, okay. In this case, these two are linearly independent, okay. Any superposition of these, of course, is also a solution, okay. But it might be the case that even though your nu's are not integers, but the difference between them is an integer. So for example, nu can be half, and then the other root is minus half. The difference between them is an integer. In such a case, it turns out that you have essentially that j nu and j minus nu are still linearly independent, okay, fine. And then you have the third case where nu is an integer, okay. In that case, it turns out that j nu of x and j of minus nu of x, okay, the power series corresponding to the value of r is equal to nu, and the power series corresponding to r is equal to minus nu, these are not linearly independent, okay. Because if you know one, it turns out you can immediately figure out the other one, okay. They just differ by some factor, okay, if nu is an integer. But then but if you know one solution, you know one independent solution, you can always construct the other independent solution, okay. And then the second independent solution is essentially known as the Bessel function, of the second kind, okay, right. It's also known as the Newman function. It's also known as the Weber function, if I'm not mistaken, okay. So you have essentially these functions are relatively well behaved at x is equal to 0, okay. They are well behaved at x is equal to 0. It turns out that the Bessel function of the second kind are not well behaved at x is equal to 0. So in many cases you don't consider those solutions, okay, because they blow up at x is equal to 0, okay, right. So that's essentially what we have for ordering differential equations. So if you have any problems, I'll be uploading the homework soon enough, okay. If you have any problems, please email me, okay. You need to be proactive, okay. I feel that essentially you're not chasing me enough, okay. I'm trying not to chase you guys too much because I don't want to. I know all of you are stressed. I know all of you feel overburdened. I don't want to burden you further, okay. But you need to take this course more seriously, I feel, okay.